So let's start. So we were looking at synchronization when we have multi-threaded programs. So we were looking at this very nice visualization tool, progress graphs. And if we map the instructions, including the critical section, including the critical section of each thread on this two-dimensional graph, we get this intersection of the critical sections of two threads which forms an unsafe region. And the claim is that when you're writing concurrent programs with multiple threads, a trajectory on this coordinate plane, Cartesian plane, is correct. Many trajectories are feasible. The kernel can schedule threads in any possible way. You could have any interleaving of instructions from the critical section of two threads. But a trajectory would lead to correct output if it is safe. And a safe trajectory is that does not enter the unsafe region. As long as you sort of skirt the boundary of this unsafe region, that's all right. But when you enter the unsafe region, there is a potential for incorrect execution. In fact, it would lead to incorrect execution. So the goal of writing correct concurrent programs is to enforce safe trajectories. Now, user programs are not in charge of scheduling decisions. And we are writing multi-threaded programs, threads, when we have multiple threads. So somehow we have to inform the kernel, enforce the kernel to stay out of this unsafe region. And the classical way to do it is using semaphores. So we have to enforce mutual exclusion, and that will help us guarantee a safe trajectory. And we must synchronize the execution of threads using what we are going to study from the Dutch scientist Dijkstra, who came up with that idea, semaphores. There are other approaches, mutex and condition variables that are part of the pthread library that we will look at in the next week's lab. And other programming languages provide, Java, for instance, provide monitors. So what's a semaphore? It's a non-negative global integer synchronization variable. So it's just a variable. It's a special variable. It's non-negative. It cannot be negative. And there it is manipulated using only two operations, P and V operations. We'll call them P and V from Dutch, some words in Dutch, but we're just going to call them P and V. So what is a P operation? A P operation is, so the semaphore variable is S, which is a non-zero integer. And the P operation is, if S is non-zero, then decrement S by 1, decrement S by 1, and return right away, right? And the operations test and decrement happen atomically. So this is support that is provided by the underlying hardware, right? So we don't have load operation, update operation, and store operation. We have, somehow we have this primitive, hardware primitive that does this test and decrement atomically. So testing, if S is non-zero, that's a test. And then this minus minus decrement is a sort of the other thing that happens. And these two operations happen atomically using special hardware support, special instructions. On the other hand, if S is 0, then suspend the thread until S becomes non-zero. So the thread will suspend itself until S becomes non-zero. That's the one thing that will happen if S is 0. And the thread will remain suspended until it is restarted by a V operation. So there are two operations, P and V.
Would the operation be done by a different thread?
Yes, possibly, or the same thread.
How is itself?
The kernel will do that. So P and V are system calls. They go inside the kernel, and the kernel has the capability. The question is, how will the thread suspend itself? These are system calls. I should have said that. And once you make a system call, you trap inside the kernel, and the kernel has full control over whatever the thread is doing. It can suspend the execution of the thread. It can preempt a thread, start another thread. So it can do all those things. And after restarting, the P operation decrements S and returns control to the caller. Okay, so these are the semantics, the meaning of the P operation. The V operation does the opposite, increments S by 1, and the increment operation, once again, happens atomically. Okay. And the other thing the V operation does, if there are any threads blocked on P, waiting for S to become non-zero, it restarts exactly one of those threads. And which one of the threads it restarts is not specified. It's implementation dependent, whatever the kernel chooses, whatever heuristic the kernel uses. And which then completes the P operation of the thread that is waiting on the semaphore S, and that thread waiting on the semaphore then decrements S and returns immediately. Okay, so these are the operations. It's a bit different. It's a bit confusing the first time you look at them, but together they provide mutual exclusion. They provide exclusive access to a critical section. Okay, so we will use P and V operations to rewrite our example from the previous lecture where we have this bad count. We did that in detail. So this for loop that was counting how many elements there are when the user types n iterations. So sometimes we get bad count because multiple threads will execute the count plus plus at the same time. They will be interleaving of the critical section. These three instructions. So we will now use the P and V operations to provide mutual exclusion to this critical section with respect to count. So with that, we will always end up with an execution like this. Or the purple could be first and green could be second. But the P and V operations will allow us to never end up with a sequentially consistent interleaving of instructions that look like this, where the instructions in the critical sections or the critical sections are interleaved. So this is the mutual exclusion we are looking for from the semaphore. And the semaphore invariant is that S is always, if we read through P and V operations, we see that S cannot be negative. S will always be greater than 0. The only P operation is the one that decrements S, but the moment S is 0, the thread suspends itself. It stops execution, and it waits for a V operation to restart. So the header file that provides the semaphore operations is semaphore.h. This is from the POSIX standard. So to initialize a semaphore, we use sem init. The middle argument will be 0. We don't want to get into that until later. The semaphore, the address of the semaphore, and the value of the semaphore, the initial value of the semaphore. And then the wait operation is the P operation, and the post operation is the wait operation is the P operation, and the post operation is the V operation. So in cs.app.h, we have wrappers for these two functions. Wait means, in case the semaphore is 0, wait for it to become non-zero. Post means if someone is waiting for the semaphore to become non-zero, post a value, wake them up. So these are the P and V operations. And what we're going to do here, so this is the bad count once again. So how can we fix this using semaphores? So using semaphores for mutual exclusion, we are going to associate a unique semaphore mutex, initially 1, with a shared variable. And we are going to surround the critical sections with P mutex and V mutex operations. So a binary semaphore is one whose value is always 0 or 1. It flip-flops between 0 and 1. You can also have counting semaphores that go up to some value n. So a mutex, so historically we call a binary semaphore a mutex, and the P operation is called locking the mutex, and the V operation is called unlocking or releasing the mutex. So threads lock the mutex or unlock/release the mutex. And when a thread locks a mutex and it's executing the critical section, we say that the thread is holding the mutex. And then there are counting semaphores used as a counter for a set of available resources. So let's just first limit ourselves to mutexes that are binary semaphores. The value could be 0 or 1. we initialize the semaphore to 1, and then the thread that comes first locks the mutex, sets the value to 0, and then unlocks it. So here we have the semaphore mutex. So we create it using the type sem_t. We have the count variable from the previous example. So we initialize the mutex. The middle argument is always 0. We provide the address of the mutex to initialize the semaphore to 1. And what we are going to do here is we're going to surround the critical section. So remember, this one statement in C translates to 3 assembly instructions that form the critical section. So we're going to surround the semaphore with the P and V operations. And then if we run this, no matter how many times we run this, it leads to the correct output. Because the P and V operations provide mutual exclusion. Only one thread can enter the critical section at any given time. There is no way anymore for the situation where the instructions from the 2 critical sections could interleave. So if we go back to our progress graphs, let's now insert the P and V operations. So these are our 2 threads, one on the x-axis and one on the y-axis. So we're going to insert P and V operations. We're going to surround the critical section with P and V operations in both cases, okay? So, and then the integers on this 0 and 1 are the values of the semaphore at any given state, okay? At any given state. And once again, this is the unsafe region because this is the critical section. This is one thread executing the critical section. This is the other thread executing the critical section. And the intersection is the unsafe region. If we enter the unsafe region, something will go wrong. We don't want to interleave the instructions from. Okay. So initially, the semaphore is 1. Now, the thread 1 executes the head of the loop, and then it executes the P operation. It performs a P operation. When it performs a P operation, the semaphore becomes 0 because the definition of the semantics of the P operation are if the semaphore is greater than 0, decrement it and return immediately. And then it starts executing the critical section. Now imagine if thread 2 then executes the head of the loop, the semaphore is still 0. And let's say the thread then executes the P operation. If the thread does not suspend, if the thread is not suspended by the kernel, the next state would be this one. But this is -1. And the semaphore invariant is that semaphore cannot be, S cannot be negative. S is always non-negative. And so this state, where all the states where semaphore is -1 are all unreachable. The kernel will not allow that. This is the meaning of the P operation, that if the semaphore is 0, the thread will suspend itself. So none of these states are possible anymore because they correspond to a semaphore value of -1, which is not possible. Similarly, if you go from this direction, so thread 2 executes the head, then it performs a P operation, making semaphore 0. There's a load. And now if thread 1 does the head, now it cannot execute the P operation because the semaphore is 0. Thread 1 will suspend itself and wait for a V operation. So the only trajectories, so one trajectory that is correct is you go all the way here, you do a V, which makes a semaphore, so right here, which makes a semaphore 1, and then thread 2 can do the P and V operations. So this clearly shows that we do achieve mutual exclusion with the P and V operations. And so P and V here is called by the same thread in the thread routine. One of the many threads trying to execute the P operation will end up executing it first. So the kernel will serialize the execution of all the P operations. So if 2 threads try to execute the P operation at the same time, the kernel will serialize the execution of the P operations. So only one thread will execute the P operation. And then if we look at the progress graph, this will ensure, mutual exclusion in the critical section. For the critical section. All right. So are there any questions about that? So far, summarizing from the previous lecture, programmers need a clear model of how variables are shared by threads. So you should be able to reason about which variables are shared using the analysis we did in the previous lecture. And the variables that are shared, they must be protected to ensure mutually exclusive access. That's what we've seen today. And semaphores are a basic mechanism for enforcing mutual exclusion. So these are the same slides that I used. So here we have used mutex, which is a binary semaphore, can only have a value of 0 or 1 to protect a critical section. So let's see now examples of counting semaphores or programming patterns where we need to coordinate access to shared resources, not just a critical section. For instance, coordinating access to a shared buffer, coordinating access to a shared cache, to a shared region of memory, a resource. So the 2 examples that we're going to look at are the producer-consumer problem and the readers-writers problem. So the producer-consumer problem is we have a shared buffer. This buffer is, think of it as just a malloc region on the heap. Let's say it's an array with a bounded, it's bounded. The number of entries are finite. And we have a producer thread that's inserting something in the shared buffer, and we have a consumer thread that is removing something from the buffer. Now it's not as simple as using a mutex to prevent writes to this buffer by the 2 threads simultaneously. We also have to schedule accesses to the buffer. For instance, the buffer may be empty. So the consumer need to wait for something to arrive in the buffer. The buffer may be full, so the producer need to wait to insert something, right? We need more than a mutex to make that happen. The real-life examples of producer-consumer are a lot. So in multimedia processing, producer might be creating videos and consumer might be rendering them on the graphical output on the screen. And if there is if one of them is slow, then we need a buffer. If the producer is slow or if the consumer is slow, we need a buffer to store all the videos that are frames that are not yet processed. Another example is event-driven graphical user interfaces, where when we, producer detects mouse clicks and other movements from IO devices, and they inserts them in a buffer, and someone removes those events and do something on the graphical output or whatever. Retrieves events from the buffer and paints the display. And all right. So we will also look at a producer-consumer model. We'll use this model to re-implement our concurrent server, where the master thread will just insert connected descriptors in a buffer, and a pool of worker threads will just remove the connected descriptors and communicate with the clients. So this producer-consumer model is really versatile. So what we need is, we have an n-element buffer. It's bounded. It's not infinite, so we have to manage it properly. So a mutex will ensure mutually exclusive access to the buffer, so the readers and writers can we don't want them to access the same element at the same time. And then we'll have two counting semaphores, one slots that count the available slots in the buffer, and the other one items that count the available items in the buffer. Okay. And we're going to see an implementation using the shared buffer package, sbuf. So let's talk about the sbuf package that implements this producer-consumer. So we have a shared buffer. Is this an integer here? It's an integer buffer. They have the maximum number of slots. We maintain the front. It's a circular buffer. It wraps around itself when it's full. So there's a front, there's a rear, and then we have this mutex to protect accesses to the buffer. And then we have two counting semaphores, one for counting the slots and one for counting the items. And we have an initialization method. dinit does the reverse of initialization. So it reclaims the resources being used by the buffer. So which is basically just freeing up whatever is malloc here. And then we have two important functions, insert and remove. So initialization and deinitialization or destruction is simple. So here's a buffer, and we want to allocate n elements initially, and calloc zeros the elements that it returns. Unlike malloc, it zeros the whatever memory it returns. So this is something that the user of this package would call and will provide the number of elements they want. So we'll take that and store it. The front and rear are both 0 initially, so that's an empty buffer. The front and the rear both point to element number 0, and then we initialize the mutex to 1 as before. It's a binary semaphore. Slots to n. We want to count slots. So initially there are every slot is empty. So there are n empty slots. So we initialize the semaphore to n. And there are no elements in the buffer. So we initialize the items semaphore to 0. So how do we write insert? So in insert, the buffer might be full at any given point. And so we cannot insert if the buffer is full. So we want to wait for a slot to become available. Now, if the semaphore is greater than 0, it means that a slot is available, right? So the P operation will return immediately. Otherwise, it will suspend itself and someone else will wake it up. So so if there is no slot, if this is 0, if this semaphore is 0, then this operation will suspend the producer. Producer is the one inserting. So how will this unblock? Who will restart it? The consumer. The consumer thread will remove an entry. The one that is removing the elements and consuming them will do a V operation on slots. So that answers your question. You know, when we want mutual exclusion, the same thread, in the same thread routine, we enclose the critical section between P and V operations. Here, we have the P operation on the slots in one function, in one routine, and we have the V operation in the consumer's routine, which is the one removing. So now we want to use the mutex to protect writes to the buffer. While we are writing, we don't want the consumer to read something partial, something broken. We want to protect writes to the buffer. And so what's happening inside index, it's a modulo operation. It's just dividing by it's taking the remainder of the number of elements in the buffer and adding 1. So it's inserting at the rear, at the back end. Okay. Now when it inserts something, it releases the mutex because it doesn't need it anymore. It does a post operation. It does a V operation to announce the availability of an item. It does the V operation on a different semaphore. That's counting the number of items that are available inside the buffer. So we haven't seen the P operation yet on items, but we have an intuition why it is here. So the consumer needs some items to consume, right? That's what it does. And consumer needs to wait for an item. There may be no item in the buffer at any given point. So the consumer will do the P operation on items, right? And it will suspend itself until an item is available. But the producer does its part of the deal and increments the item semaphore atomically to announce the availability of an item in the buffer. Okay, so very simple. You know, concurrent programming. It's in terms of lines of code or complexity. It doesn't look very it doesn't look a lot of lines, but it's subtle. You have to be careful where to insert the mutex, where to insert the P and V operations. So now remember this picture of the insert function in your head, and we are going to look at the remove operation. So the remove operation takes removes an element from the buffer and returns the integer. So here's the return item. So we have an item that we're going to read from the buffer. So here is the read. So here's the read inside the critical section. So here, this routine will be run by the consumer thread. That's a different thread than the producer thread. And this routine, so here, the consumer waits for an item. If P is non-zero, it will just return immediately and just do its work. Fine, good. But if P is 0, it will suspend itself and wait for a corresponding V operation on the counting semaphore items, all right? And that V operation is performed by the producer. We already saw that right here. That's the V operation on the counting semaphore items, and here's a P operation on the counting semaphore items. And then, like I said, when the consumer removes an element from the array, it announces the availability of a slot using the V operation. So if the producer is waiting for an empty slot, in case the buffer is full, the consumer is informing the producer, look, there is an empty slot available. And it does using the atomic V operation. So this is our producer consumer implementation of the producer consumer. And you could have anything here instead of integers. And you might need that in the last lab and the assignment. You might need this boundary buffer to store whatever you want to store, a web page or something as a cache or. Okay, so it's pretty general, but here we're just using the int type to demonstrate. Okay, so so I hope this is clear. I hope that by now you have some, more intuition about the P and V operations, and we can use them to solve a variety of problems, not just a providing mutual exclusion for a critical section. So let's look at a generalization of the mutual exclusion problem. Okay, so this is more general than just a critical section protected by a binary semaphore. So the problem statement is the reader threads only read the object. So we have a number of threads. The reader threads only read the object. The writer threads modify the object. Writers must have exclusive access to the object, and unlimited number of readers can access the object. So imagine there are no writers. Right? And we have 100 readers. We don't care. We don't want to serialize the readers. And unlimited number of readers can access the object. These are just loads. These are just reads. We are not afraid. We can let many readers access the whatever that object is. But if there's a writer present, they should have an exclusive access to the object. No reader should be able to enter. Now, this situation occurs frequently in real systems, online airline reservation system, where a lot of people can look at the available seats at any given point, but only one can reserve the seat for themselves, right? So we don't want multiple potential travelers to reserve the same seat and then fight for it inside the plane. We want to make sure that they can all see what seats are available, but only one of them is able to reserve the seat. And then when you write the multi-threaded caching web proxy, there'll be a lot of client threads serving the client requests on behalf of the sorry, a lot of proxy threads serving on behalf of the clients. And we'll ask you to cache whatever you bring from the server. And you want to make sure that the cache is, managed properly. If there are multiple threads trying to read something from the cache to avoid going to the server, they have access. But if there's a writer trying to bring something inside the cache, we lock properly the cache object. So there are two variants of this readers writers problem. The first one is, now you can imagine if we have a number of readers and a number of writers, we can create priorities. We can say that the writers can wait. We are not interested in admitting new information inside the object, but we want the readers to go ahead. We don't want to starve the readers. We want to prioritize the readers. Or we can have a different policy saying, if someone wants to write, that should happen as soon as possible. And the readers can just wait. Maybe because we want the readers to read the most up-to-date up-to-date state of the object, or some other reason. And in both cases, so the first readers writers problem favors readers. Okay. No reader should be kept waiting unless a writer has already been granted permission to the object, to use the object. If the writer has been granted permission, the reader must wait. There is no other way. We want to provide mutual exclusion. So if there's a writer with access already, we need to wait. Otherwise, just because there is a waiting writer which doesn't have access yet, we should not stop the readers from doing their work. Okay, so we should favor the readers in the first problem. The second problem favors writers. Once a writer is ready to write, it performs its write as soon as possible. So a reader that arrives after a writer must wait, even if the writer is also waiting. So if the writers are waiting and the readers are waiting, we prioritize the writers. And in both cases, starvation is possible. If you always prioritize readers and you have readers that keep coming, the writers will never have a chance to do their work. And that's starvation with respect to writers. And if you are always, so when we bring new information, we call it admission. So when we are admitting new things, our admission policy is to admit things as soon as possible, then we may starve readers. So let's see an implementation of where we favor the readers over writers. And then you'll do the other one as an exercise. So in this one, we are going to see an implementation of the first reader-writer problem. So we have a global variable read count, and we have a semaphore mutex w. Sorry, we have a semaphore mutex and w. So we have two semaphores, and they're both initially 1. Okay. So let's look at the writer first, which is easy. The writer just uses the W mutex and P and V operations to protect the critical section. Okay, easy. So we need that. So W stands for writing. So whenever you want to write something, you use the W mutex to protect the critical section. Because while a write is going on, we don't want the readers to read at the same time. On the other hand, the readers use the other mutex called mutex to protect this critical section where, with respect to read count. So readers grab the mutex, increment read count, And the first reader, remember, we are favoring the readers in this implementation. This is a solution to the first problem. If it is the first reader to enter the critical section, we lock the, we do a P operation on the W semaphore, right? We grab the lock on the critical section. This critical section. Okay. And then it unlocks the mutex because it doesn't need it anymore. When it is, sorry, it's not this one, it's this one. So the W, where it reads something that is being written here. So, and then there is, when it is done reading, it decrements read count. And only if the read count is 0, the thread, the last thread that executes the critical section does a V operation to wake up the writer. Okay. So once again, so here's a critical section that we want to protect. So the reader is reading something here, and the writer is writing something here. Okay. So this is simple. P and V operations on the W mutex. This is a little bit more because we want to favor the readers. The first reader locks the mutex, and any reader that comes after this reader will just read whatever they want to read. They will enter the critical section without any interference. And so the readers will keep coming while the writer will have to wait, because the first reader, when read count was 1, the reader grabbed the lock, and the lock is released only when read count is 0. So each reader, before leaving, decrements read count minus minus, and when read count is 0, the lock is finally released. So the first reader to enter the critical section locks W, and the last reader to leave the critical section unlocks it. So writer during all this time will keep waiting, okay, for the W mutex. So readers will hold the mutex, hold the lock, as long as they are in the pipeline. So this is one way to implement the reader writers.
Should read count be modified, or is that?
It's protected by the. So this is global. This is not on the stack anyway. So volatile is used to, sorry, no, this could be in the register. No, it's because it's protected by the mutex. So there is a mutex to protect it, so we don't need it to be volatile. Are there any questions about this? Right, we could do that. Right. So if we have multiple cores and the writer is waiting, the kernel could decide, because P and V are system calls, so the kernel knows that this thread is waiting on a V operation. It could decide, look, I want to schedule something else. But it's a bit hard for the kernel because V operation might happen right away, and then the context switching, the scheduling of a different thread, and all that, you know. So writer might need to wait forever then to. So if you look at this example offline, just remember that the first thread here is locking the mutex, and the last one here is unlocking the mutex. The W mutex is the one that provides mutual exclusion for the critical sections, where we are reading a shared resource. Okay, let's build a variant of the concurrent servers that we've been looking at. We looked at a process-based server, an event-based server, a threaded server, and now we are going to look at what we call pre-threaded concurrent server. Pre-threaded. Now, the key idea is that in a thread-based server, we create a thread, we create a p-thread whenever the main thread accepts a connection request. So every time we have a new client, we create a p-thread. So for servers that run for days, months, this is very inefficient. So pthread create has an overhead, and we might want to bound the number of threads that we want in a system at any given point. We might want to have, let's say we have a system that costs something, it's a mid-range server, and we don't want many client threads at the same time. We want to have a pool of threads, let's say 100 threads, and that's it. And we don't want to go above that point. So here's one way to do things differently. So what we're going to do is we're going to have a master thread that will accept connections from clients. And you know that you get the connected file descriptor. The master is listening, and whenever there is an accept, whenever it accepts a connection, it gets a connected file descriptor. So this time the master is not going to create a pthread, it's going to insert the connected file descriptor into a buffer. So the master thread is a producer of connected file descriptors. It's going to produce connected file descriptors by going in this iterative while loop, connecting, accepting connections. And we'll have a pool of worker threads. We will have a pool of worker threads that we will pre-create. We will create these worker threads beforehand. We will not wait for a connection request to arrive to call pthread create. We will have them in our pool. Like it's called pooling. So, and whenever there is something in the buffer, one of the worker threads will remove something, remove the connected file descriptor from the buffer and service the client. Okay, so this is a more efficient and more sort of elegant way of building concurrent web servers. And this is called pre-threaded. So this is very important. Pre-threaded because we don't wait for the client to arrive, or we don't wait for to create the thread. We create the threads beforehand. We'll see that. We have a pool of threads that we create even before any connection arrives. Okay. So this is blah blah blah. We do this every time. So we get a listening file descriptor. And then we initialize our the sbuff package. So we have some constant number of clients that we want to bound our buffer to. We don't want to handle more than this many connected file descriptors. And then we have an sbuff. We have a semaphore sbuff. And so here, before this while loop, previously, we were creating threads inside the while loop every time we accept a new connection. This time, we are creating all the threads. So we're creating a thread pool beforehand. And this will come handy. So these are our worker threads that will do the job for us. And the thread routine, we give them all the same thread routine, okay? So inside the while loop, we do this every time, we do an except. Now this time, the master thread has much less work to do for each client. So this is a one-time cost. So this is a one-time cost. You do this at the start of the year, and for the rest of the year that your web server is running, it doesn't have to do that, okay? But the servers don't run for years. There's usually some security patches and binary shutdowns and all that. Anyway, so you get the connected file descriptor, and this time the master thread is just inserting, using our sbuff insert routine, is just inserting the connected file descriptor inside the inside this buffer of file descriptors. That's all it is doing, okay? Now the thread routine, first of all, the thread detaches itself, and then all it is doing is it's removing a connected file descriptor from the shared buffer of descriptors. It's doing that echo. It starts playing echo with the client, and then it closes the file, connected file descriptor. So all the worker threads are doing this, and one of them at any given point will grab the connected file descriptor when it is available. So if you have 100 clients that are waiting inside the buffer, and you have 100, or let's say you have 10 worker threads, then each one will at some point grab, as long as the buffer is not empty, each one will grab something from the buffer and service a client. So, all right. So here we are using the sbuffer remove to get a connected file descriptor. Here we are using sbuff insert, and everything else, the counting semaphores and everything is sort of encapsulated inside the abstracted way by this package sbuff that we wrote. Okay, so are there any questions about this? Because this is important. This is how you're going to write the web proxy. Right. Right here. So there's a type def, and then the initialize. When we initialize, we create the memory resources that we need to store the semaphores and everything. So that should all be enough up to this point, hopefully, for you to do the assignment, and I'll release it in the evening because I want you to cover all this before you can do the assignment. Otherwise, there's no point. So now we're going to discuss thread safety, and this is an important concept. When you're writing multi-threaded applications, you need to know that if the function you're using is thread safe or not. So a function is thread safe if it always produces a correct results when repeatedly called from multiple concurrent threads. So if you call a function from the same thread, hopefully it's always correct. A thread safe function is one which you can call from multiple threads and you get the correct results. So this may be surprising, but there's a number of reasons why threads that are part of standard libraries or threads that others write are not safe to use in multi-threaded applications. So we're going to study 4 classes of thread unsafe functions. So why do people write thread unsafe functions? Well, it's partly historical. Threading pthreads came after. The idea of threads came after, standard C library was written and all that. So class 1 are functions that we have seen, that do not protect shared variables. They don't use mutexes to protect shared variables. Clearly, these threads are not safe to use in multi-threaded applications. And we have seen examples of thread routines, bad count, others that are not thread safe. Functions that keep state across multiple invocations. So internally, if a function uses, for instance, a static variable, and the output depends on the previous state of that variable, then that function, if it is called from multiple threads, is not safe to use, because two threads will, there's only one state, but two threads want multiple instances of that state, which is not available. Class 3 is one where functions that return a pointer to a static variable. So historically, for some reasons, there were functions that were written that always return the address of a static variable. And then the user can dereference the static variable and do something. But when multi-threading came, these functions suddenly became unsafe. If two functions have a pointer to the same static variable, there are problems. And class 4 is the easiest to understand. Functions that call thread unsafe functions are not safe themselves. So we've seen the example. If you don't protect shared variables, the function is not thread safe. The fix is easy. Well, it depends who you ask. Use P and V semaphore operations. Example is goodCount.c. The problem is that, so one reason sometimes they don't use P and V operations is these are system calls. You trap inside the kernel whenever there's a P operation and V operation, and that's an expensive operation. There's a there's a system call, there's a trap, and then the CPU jumps to a different instruction somewhere in memory, and then a lot of things happen. So there is a cost of synchronization. These are not user level functions. These are not just you don't just initialize a new stack. You actually trap inside the kernel. You change the mode bit from 0 to, from user to kernel, and you do a lot of other things. Class 2, so relying on persistent state. So relying on persistent state across multiple function invocations. So here's an example of a pseudo random number generator. It's pseudo because each time you give it the same seed, it generates the same sequence of random numbers. When you give it a different seed, it generates a different sequence of random numbers. So for debugging and all that, it makes it easy if you have this property of pseudo randomness, where if the seed does not change, you get the same sequence of random numbers. So here's an implementation from the C library. At least at some point they had that, where you initialize a seed using this function srand. So you pass the seed that you're interested in, and then this function sets a global variable, static variable, to seed. Actually, this reminds me, I said something wrong in the last lecture. So global variables don't have, C is a little bit confusing at times. It uses the same, thing for different purposes. So static here, it just limits the scope of the variable next to this specific file. If you have multiple files in your project, you want to make this variable private to this file, static will give you that. Okay. And then it has a different meaning when you use it inside the function, that the storage duration of that variable is static, meaning it will last the eternity of the duration of the program. So inside, you can see that the rand function, so then you call rand, the user first sets a seed, which sets next to something, and then the user calls ran to get a random number. So inside, the number it's returning you is a function of next, and next is a function of its previous value. So this function ran is maintaining some state. So if you call this function from two different threads, they are not going to see a sequence of random numbers corresponding to their specific seed. It's not obvious what they will see, because there's only one next, and it depends on the seed. So if multiple threads are using a different seed, they will not see the same sequence of values. This is a thread unsafe function because it maintains persistent state across multiple function invocations. So to make it thread safe, we can do one thing to make it thread safe. We can make it the responsibility of the user of the function to actually maintain the state. So the user has to store the state, whatever is returned, and then pass it to the function. So this way we take the state that was stored outside the function, that the program that is using it, to inside the program. So previously it was stored inside this library or whatever, this package. So we take next out, and we make it the responsibility of whoever is using this function to remember the state next and provide it each time the random function is called. So that's more work for the user of the function, but it makes a function thread safe. So programmer using this, so we call it _r, must maintain the seed and provide it each time, right? All right, so this is a little bit more involved. So this is a class of functions that return a pointer to a static variable. They always return a pointer to the same variable, right? So for instance, there's a function called ctime. What it returns is a pointer to a structure that it contains. But it always returns the pointer to the same. It doesn't allocate a new structure on the heap. It has one structure internally, and it returns a pointer. It fills it up whenever you call ctime, and it returns a pointer to the same function. And that is problematic. If two threads have a pointer to the same static variable, that's a problem. So what the fix is, the first fix is the same as seen. Rewrite the function so caller passes address of the variable to store the result, right? So make it the responsibility of the user of the function to provide a pointer to a structure that the ctime function can then fill in. So ctime function returns some structure that you can use to print the time, the current time of day or something. But you may not have the code of the function available. So if you're using the C library, you cannot go and rewrite the C library. And if you change the ctime function, then you might have to change it in many different places. It might break your program. So the other fix they use is what they call lock and copy. Okay, so we write a new wrapper function that is thread safe. So first of all, we use a mutex to synchronize accesses to the ctime function. So only one thread can call ctime at any given point. So we enclose this all in a mutex. using P and V operations. So whatever we get, so we get a pointer to the same static variable that C time returns every time you call it, and we copy it into a different variable. So here we are doing a str copy. We're copying shared whatever is C time is returning into another variable, and that variable is provided by the user of the C time function. All right, so this is lock and copy. You lock, you use a lock, so only one thread calls C time, and whatever is returned by C time, before you unlock the critical section, you copy that result in a different variable. But this copy might be very expensive. In fact, there is something called, it's not just a copying a variable. This might be what is called a deep copy. So if you have a struct that contains a pointer to another struct, and that struct contains a pointer to another struct, and you have sort of this linked structures, then you need to traverse and copy everything, and that may be very expensive. So the thread-safe variants of some of the C library functions, you might notice at some point in your, at some point that they are really very slow because of this reason. So lock and copy. Okay, threads. So threads that call unsafe functions, well, modify them to call thread-safe functions only. That's the only way. There is a subset of thread-safe functions called reentrant functions. And a function is reentrant if it accesses no shared variables when called by multiple threads. So reentrant functions, by definition, require no synchronization operations. Okay. And sometimes reentrant functions are useful. Sometimes they are required, for instance, when you're writing signal handlers. And sometimes you want to know what class of functions are reentrant so you can avoid the synchronization overhead. Remember again that synchronization has a very high overhead because of the P and V operations. The only way to get to protect a critical section is to inform the kernel that this is the critical section that you want to protect. So most functions in the standard C library are thread safe, malloc free, printf, scanf, and there are some exceptions, ctime and others. So this table, the functions that you will use, whatever time remains in this course, would be thread safe. So there's a couple of things that I want to finish off. So we have looked at races before. Let's look at once again. So a race occurs when correctness of the program depends on one thread reaching point X before another thread reaches point Y. So this is more like you're depending on the temporal properties of the machine to ensure correctness. But temporal correctness is not a provable property. You cannot rely on, I think this thing will happen fast and this thing will happen slow, and so my program is correct. This is not. At some point, your program will break because of this assumption. So in a for loop here, we are creating a number of threads, and we are giving each thread an argument I, the address of I. And in the for loop, the I happens to be also the loop counter. So I is changing. So there's a race between I++, and inside the thread routine, the thread gets an ID by dereferencing I. This is contrived. This is, you shouldn't write programs like that, but I want to make a point here. So once again, when we create a thread, this is a routine that we want to run. And as argument, we give the address of I. This address of the I on the stack, and then the thread dereferences that address to get its ID. So it's getting I basically, I equals 0, 1, 2. And then we print a message, hello from thread, my ID. So if everything works correctly, we will always see hello from thread 0, 0, hello from thread 0, hello from thread 1. We will never see hello from thread 0, hello from thread 0, hello from thread 1, hello from thread 1, hello from thread 1. We'll never see that, right? We only have one instance of each. But there is a clear race. There is I++ going on here. So if this thread is preempted and scheduled out by the kernel, but the main thread keeps running, then when this thread starts running again, it will say a different ID. Okay, so there's a race. So main thread is doing I+1, and peer thread is dereferencing, and this is a race. This is a race of what happens first. And this is not provable, this is not correct. This will at some point always break. So the race between increment of I in main thread and dereferencing of the variable, the argument of the peer thread. And the way we fix that, so the question is, does this really happen? So we are going to see some empirical data on different machines, and we'll gain some insight into the behavior of races. So if there's no race, then each thread would get a different value of I. So we'll see unique I values on the output. And the values that we save, let's say in a file, after running this program, would go through 0 through 99. So this is a execution with no race, right? This is what we expect. So this is a histogram. And on the y-axis, we are showing how many times we see a specific value. Now, if there is no race, we should see each value only once, right? And so this is a histogram with no race. So if we run this program on a single core laptop, we see that some values are repeated. But most of the time, we get the correct value. There is a race, there's a clear race, because it's a single core machine, it's not really happening that frequently, because one thread runs at a time, and then somehow the temporal nature of the interaction between the bad code example that we have and the single core, the race is not that frequent. If we run it on a multi-core server with lots of cores, and each thread is running, many threads are running in parallel. We have parallelism on top of concurrency. Most of the time, we get bad results. Most of the time, we see that there is a race, because things are happening really fast. All threads are running independently at the same time. There's parallelism, and this is a problem with races. You run it on a different machine, you see more instances of a race. You may not even see a race. You may run it on your phone or on a very slow processor. You may never actually see a race. But in production, someone runs the same code on their machine and there's a race, right? So that's why you have races, bugs that are due to races in production software a lot of times. So anyone remembers what we did? We've seen this race before when we had a connected file descriptor, and if we give the peer thread the address of the connected file descriptor, we had a problem, but we did something to prevent that. What was that?
Just talking in like the value of I directly.
All right, so that's one solution. Pass by copy. What we did there was we do a malloc. We allocate an integer on the heap, and then we set the value to 1, and we pass the pointer. Passing the value it's okay, that it affects readability. So what is expected here really is a pointer. Now we could pass a pointer, or we could pass an integer, and we can cast it as a pointer. It's just an address, right? It's a pointer is just an address, and that's what an integer is. And someone reading your code may not look at what you are doing in the main routine, and they might look at the thread, and it's a little bit confusing. So here we are solving it by allocating the variable on the heap and passing the address of the variable. So now there is no race, because for each thread we create a separate instance of I, and the responsibility of the thread routine is to free up the space taken up by I. So the other worry is if all that is not enough, there are deadlocks. So a process is deadlocked if it is waiting for a condition that will never be true. So process 1 and 2 needs 2 resources, A and B, to proceed. So process 1 or thread 1 needs A and B, and process B or thread B needs A and B. So they need 2 resources to make progress, and for some reason, we don't know. Process 1 acquires A and waits for B, and process 2 acquires B and waits for A, right? So you can imagine people writing programs at different points in time, and they do the P and V operations in such a way that in one thread, they do P and V on A first and then B, and in the other thread, they do on B first and then A. So there's no way out of this situation. So here's an example where, so this is a function thread routine count. So you're creating 2 threads. So this thread has an ID of 0, this has an ID of 1. So thread 0 is, so you have 2 mutexes, mutex 0 and mutex 1. So thread 0 is doing P0, and then it's doing P1, right? This is ID 0, this is 1 minus 0, 1. And thread 2 is doing, the thread with the ID of 1 is doing P1, and 1 minus 1, 0, P0, okay? That's an example. This is a completely contrived example. You're never going to do that. But the same thread routine is run by 2 different threads. One acquires the mutex in order 0, 1. The other acquires the mutex, the 2 mutexes in order 1, 0. And so this is a deadlock. So progress graphs are very useful to visualize deadlocks. So here's a forbidden region for S0. So this is where, so this is how we get so this is the P operation of one thread. This is the P operation of the other thread. And here is the V operation of one thread, and here's the V operation. So this is a forbidden region. So if we look at the 2 forbidden regions of S0 and S1, so what they're doing is, so one is acquiring a log S0, S1, the other one is acquiring the log S1, S0. And this is where they acquire the log. This is some initial instruction. So the other one goes in this direction. So you can see that this region here is a it has states that lead to a deadlock. Once you enter this region, there is no way out. You can enter the region as much as you like, but there is no way out, right? So let's say, so this is a deadlock region. So let's say thread 1 does something. This is just one instruction. And then it does a P operation on S0. S0 and S1 are two semaphores. And then thread 1 executes some instruction and then does a P operation on S1, okay? So now where should we go, right? This is like a video game, right? Now there's no way out. All these are -1. Semaphore has to be -1 for this thread to enter here or this thread to enter here. So thread 1 cannot enter this forbidden region. Thread 0 cannot enter this forbidden region, so they're deadlocked. So once you enter here, it's like you're trapped.
Can you go like PS1 to thread 0, then PS1 to thread 1? Like
the only way to avoid deadlocks is to acquire the locks in the same order and to release them in the same order. And that's what the student has observed. So this is a good observation.
Deadlock is like first pull injury, then pull S1. You like move one right and one up. Instead of like two right and then up.
So are you saying that if I change this to P0, P1 and
then like before you do like two movements to the right, then two movements up. But when that's the P block, like when's the example of deadlock be one movement to the right and one movement up?
also this means that PS0 has just finished. And this is some other instruction, I don't know, whatever, a starting instruction. So the way you read the progress graph is, this is where PS0 starts executing, and this is where it ends. And so this is where this line here is some instruction, we don't know what that is, just a starting instruction. This is where thread 1 will do its PS1 until this point. Right, so that's how the.
If you go back like two slides to the first forbidden region, I think it's that problem.
Right. Right, so this is a head. So this is where head starts and this is where it ends. This is where P starts and this is where P ends. This is where load starts and this is where load ends. This is how it is. All right, so the other interesting thing, let me just finish this set of slides. The other interesting thing is that, I don't know, you can never reach any state here in this region, right? So you do this exercise and you realize that no matter how hard you play, you will never reach that region over there. All right, so the solution is, so any trajectory that enters the deadlock region will eventually reach the deadlock state. Other trajectories luck out and skirt the deadlock region. So if you have a deadlock, potential for deadlock in your program, sooner or later it will happen. And it's non-deterministic. And that's a problem with concurrent programming. You run it 20 times, it works, and the next time when you submit your solution to the teacher, it won't work. But it will work on your machine. So be ready for that. So the only way to avoid deadlocks is to processes acquire locks in the same order. And the order in which the locks are released does not matter. So if we do this again, let me start with deadlocks next week. I don't want to make you stay here. All right, thank you. Okay, this was the last slide. Oh my God.